Okay, let us look at question B7 now. So figure B 7.1 shows a magnetic field lines between the poles of two magnets. So I have two magnets. Then if you look at what is happening here, we need to understand number one, the directions of the arrows, how they are moving, and the pause that can cause this kind of reaction when two magnets have been brought near to each other. So the concept here, which we're looking at what we call magnetic field lines and the magnetic field. So we need to understand the difference between magnetic field lines and a magnetic field. We know that magnetic field lines, these are lines that runs from North Pole to South, from North to South poles of a magnet. That is magnetic field lines. Wow, a magnetic field is the region. It's a region where a force is detected or experienced. So from here we'll look at the diagrams that will explain the statement. So if you have a North Pole, you have a South Pole. So since magnetic field lines, these are lines that are moving from north to south, so we are going to discover the movement in this way. So they will be moving like that. They will be moving like that. Then if you draw the diagram like this, it is incomplete because it has no arrows. So we put the arrows to indicate that they are moving from north going to south. So those are magnetic field lines. Then if you say a magnetic field, if you place any magnetic material from within this region, it will experience a force. If you place a wire here, this wire will experience a force of being attracted to a magnet. So a region where a magnetic field force is being experienced is called magnetic field. So a field is just a region where a force is experienced. If you put a wire outside this region where the magnetic field lines are passing, no force will be detected here because there are no magnetic field lines passing through this region. As a result, this is not a magnetic field. Then the other aspect we can look at is to understand what we call the properties of magnetic field lines. So what are these properties? Number one, we need to understand that these magnetic field lines, the common one is they do not cross each other. Then the other one is they run from north to south. Then the other one will say the more the magnetic field lines, the stronger the magnet. The stronger the magnet. Okay, so from here we can see that these lines, they are not crossing each other. Then the more the magnetic field lines indicate that the magnet is strong. So how do they behave when they come into contact with other magnets? So we have let's say we have this north south. We also have another magnet which is north south. So if you look at these two magnets, you're going to discover that from north and south, the magnetic field lines will start now moving from north coming to south like this. So they will be behaving in that order. They will be behaving in that order. So even these ones, they will be moving like this, coming to south. They behave in this order. So that is what will happen when two magnets are into contact, where there's a north pole and a south pole. So the lines will be moving from north going to south. Then the next stage, we'll try to demonstrate using north and north. So the behavior of north and north will show the same behavior in south and south. So since north and north, these are like poles, according to the law of magnetism, we know that the law of magnetism states that like poles repel while unlike poles attracts. So what will happen here is that these will be moving like that. Also, these will be moving like that. So there will be no contact. There will be no contact at all. They will be moving. So if there is a north, there is a south, there is a north, there is a south. So they will be moving like this. Then they will be entering into the south. So they're going to leave a space here. At this point, since there are no magnetic field lines, if you place any material here, no force will be experienced. So on that point, this point where a force is not being experienced, it is called now a neutral point. So a neutral point is a point where no force is being experienced. Okay, so the same situation will happen here. Now we need to pay much attention. Look at how the arrows are moving out when there is north and north here. But if there is south and south here, we are going to discover that despite the fields are moving in this direction, the secret about this is to understand how the arrows are moving. Since they are doing like this, they are south and south, you cannot place the arrows like this because these arrows are moving from south. Then remember we said according to the properties of the magnet, we said that these magnetic field lines, they move from north to south. So if you put the arrows like this, it means that you are wrong. So the arrows must be indicated like this. The arrows must be indicated like that because they are coming to south. So this point also is called the neutral point because there is nothing which is taking place on that one. All right, so this is about the magnetic field lines and the magnetic field of a magnet. So we'll be discussing magnets in parts according to the question you're going to will be bringing. Let's go back to our question now. So figure B7.1 shows magnetic field lines between the poles of two magnets. So we have this R, then we have these two magnets, then we have the letters. So let us look at the arrows where they are going. The arrows where they are going. So if the arrows are going outside, it means this part is now the North Pole. This part is also the North Pole. But if these arrows were coming in the opposite direction like that, then we can predict to say these arrows, these poles are south and south. So name the point R. So point R, it is called neutral point. Then if P is south pole, what are the poles Q and T? So if P is south, they have also given P is south, you know that this is now north. Then if this is north, this is also north because of the arrows, then this is the south. So Q is north, straightforward. Then T is south, straightforward. Explain how soft ion keepers help magnets retain their magnetism for a longer period of time. Okay, so let's look at this. If you talk about the magnetic keepers, so magnetic keepers, we're looking at how we can retain the strength of a magnet for some time after leaving it without using the same magnet. So in short, we are saying the magnet keepers, these are keepers that are put on the edges of a magnet to retain their strength. So let's look at this diagram. We have a North Pole and a South Pole. Also this diagram, we have a North Pole and a South Pole like that. Now this magnet, now let me just start with one. This magnet, if it is left like this for some time, it will become demagnetized, or its strength will be reduced because the magnetic field lines of this magnet are now interacting with the magnetic field lines of the Earth. As a result, due to that interference, these magnetic field lines are not being kept to come and form a circuit like this. Hence, they are being interfered. But if they are forming a circuit like this, this magnet will retain its magnetism or its strength for some time. But as long as the pores of a magnet are open like this, so these magnetic field lines now, they will be moving around and interfere with other magnetic field lines from the Earth or other materials, hence reducing the strength of this magnet. So to avoid this situation, you're going to find that now a magnet like this with north and south, we are going to put the iron metal. We are going to put the iron metal or the iron bar like this. So once we put this iron bar, So iron metal. We know the properties of iron to say iron is easily magnetized and easily demagnetized. So this iron now, it will ensure that as the magnetic field lines are moving from north to south here, they are not going to move away, but they will form a circuit ring. They will form a circuit ring where the magnetic field lines from the north will enter into another ion and goes back into this magnet. Again, it will be moving just like this. So because of the magnetic field lines are not moving away from the magnet, we call these two ion metals that are doing this as magnetic keepers. So this is a keeper. It is keeping the magnetic field lines from moving away from the magnet. So these are keepers. Now, how can it do this? How can it do this? So we are saying its major function is to close the path of the magnetic field lines that to keep the strength of the same magnet. So our answer will say the magnetic keepers, they form a ring circuit of magnetic field lines that moves within a magnet and prevents with the interference. Interference of other magnetic fields. So that is how it keeps the strength of a magnet for some time. Now, magnet keepers, they connect the north pole and the south pole. So this allows the field to circulate within the ions instead of dispersing away. So these keepers, they connect the strength by keeping the magnetic field lines to move within the magnet and avoid the magnetic field lines of magnets to interact with other magnetic field lines that will reduce its strength. All right, so then so we have explained here states two differences between the iron and steel as magnetic materials. So the difference between the iron and the steel as magnetic materials, number one, we need to understand that iron is easily magnetized than in steel. So in this situation, we are saying the moment you expose iron to, so if this is a magnet, north and south, then you expose iron there, this magnet, it will induce its magnetic properties into this steel and it will be easily magnetized. Then the opposite Steel is not easily magnetized than iron. So we can also give the difference in terms of the uses. We know that iron is used, the use of iron and steel are different. For example, iron is used to make permanent magnets, while iron are used to make temporal magnet, while steel is used to make permanent magnets. Also, in terms of domain theory, when we talk about domain theory, we're talking about how the atoms in terms of in the structure of an ion. If we have a structure like this for ion, it has the particles, these atoms, which are aligned like this. So according to domain theory, once this ion is magnetized, these particles are quickly to realign themselves very fast compared to steel, hence proving that iron is easily magnetized and easily demagnetized, while steel is hard to magnetize and hard to demagnetize. Then iron is also used to make transformers and in speakers compared to steel. Then steel is also used to make permanent magnets and the other equipment that needs a lot of strength from the magnets. All right, so from here we can look at okay, so we'll just focus on question 7, then we'll also make a video on for question 8, then we will go further on to look at radioactivity. So for today we end here.